I have the pleasure of introducing myself. My name is Johan. I work here at CBU. I work mainly on fMRI methods. So this talk is going to be about how the neuroimaging measurement process shows up in multivariate analysis methods like representational similarity analysis. And the overall take-home message from this talk is going to be that they do show up. So I think there is a somewhat popular idea in the literature that as long as you're doing something multivariate with your fMRI data, for example, you're somehow getting to the neural representation more directly than you would be if you were doing something like single voxel activation mapping. And that's probably not the case. What is happening is that the measurement effects that you're seeing are showing up in a different way from what you might be used to seeing. But they're still there, and we still have to think about them. So I'm going to start by making this a little bit less abstract. I'll talk about what I mean by measurement effects. I'll do some simulations. Then I'll briefly talk about an empirical example, a published data set that I published last year that illustrates what can be happening. And I'll close on some general recommendations. In general, I'm going to talk about these measurement effects in relation to fMRI today, but similar problems will arise if you're working with MEG or EEG. The basic principle is the same. So just a recap slide for those of you who are not familiar with this. Representational similarity analysis is an analysis method where you're basically going to take your data and your models and you're going to translate them into a common currency of distance matrices. So you're going to calculate the distance matrix from your fMRI patterns by calculating something like the correlation distance between your different activation patterns to particular images in this case. And then you're going to do the same thing with your computational model. You might correlate the activations of the model in its internal state and build another distance matrix from that. And the neat thing about this approach is that once you've calculated the distance matrices, you can easily compare them to each other, right? You can just calculate a second order correlation now between the similarity matrices and do straightforward inference on which model is most similar to your data. So this is remarkably beautiful and simple, but like any remarkably beautiful and simple method, there are some assumptions going into this, as we'll discuss in detail. So the basic sort of excitement, I think, for many people about multivariate analysis is this idea that you might be able to sort of unwarp the neural code. You might be able to get something that's closer to what the neurons are actually doing, even though your functional imaging method is, of course, indirect. And so to illustrate this point, this is an old figure from Tim Andrews. This is actually to explain fMRI adaptation, but it works perfectly well for this case. So what we're looking at here is an fMRI voxel where we've observed the following result. We have a big response to this face and a weaker response to the other two conditions. And there's a large number of possible neuronal activations that could give you that set of responses in the voxel. But two classes would be all of the neurons are really doing the same thing. All of the neurons like the face a little bit more than they like the other two. Another possibility would be that you have pure selectivity. In other words, you have cells that only like the face, and you have some cells that only like the other categories. And the only reason why this voxel likes the faces more than the other two is because you happen to have more of the facey cells than of the other variety. And I hope you'll agree with me that these two, although these two are perfectly ambiguous in the fMRI voxel, for our functional interpretation, it does matter which one of these two it is, right? For our theories, it probably is important which one of these two it is. And I guess the excitement about multivariate analysis is the idea that if we had the latter case, where we have these mixed, purely selective cells, perhaps if the mixture, that is the frequency of the different cell types, is different over different voxels, if we somehow combine that evidence across multiple voxels, perhaps we can sort of pull these things apart and get something that's a little bit closer to what the neurons are doing than what you might get if you were restricted to only considering each voxel in isolation. So the idea so on a more theoretical level, the basic idea that RSA might be able to get you closer to what the neurons are doing comes from the Johnson-Lindenstrauss lemma, which I'm not qualified to tell you about in detail. But at a high level, what the Johnson-Lindenstrauss lemma proposes is that if we're in some high-dimensional space up here it's only three-dimensional, but in the real case, of course, there'll be tens of thousands of neurons, and we're going to map that to a lower dimensional representation by taking random projections through the original space. As long as those projections are random, the distance matrix that we get in our low-dimensional representation will be remarkably similar to the distance matrix for the full representation with a high probability. So more concretely, if our voxels are constructed by just taking a random projection on each neuron and creating voxels, then we should expect that we'll actually get pretty much the same distance matrix out of our fMRI RDM as we would get if we had access to all of those neurons in the population code, which we generally don't. So that sounds great, right? But the tricky bit is this, the random projection bit. Is this really a sensible measurement model? Is this how fMRI voxels are generated, by taking random projections on neurons? If it is, then this would hold and it would be fantastic, right? We could forget about single unit recording. So to make it a bit more concretely why that's probably not the case, I've done a little simulation here. So here we have 2,000 simulated neurons and their responses to 12 different images. And if we calculate a Euclidean distance matrix by taking the pairwise distances between those 12 images, we get this little distance matrix, which we can summarize using multidimensional scaling into a perfect two-dimensional solution where the stimuli are arranged in this nice little grid-like structure. So if we took those 2,000 neurons and we just took random projections and we constructed 20 fMRI voxels, it turns out that you get almost exactly the same distance matrix by analyzing the distances among the 20 voxels, and the MDS solution, of course, is the same as well. So if this random projection logic held, then this would be beautiful, right? We could just use RSA to say that, well, we're indexing into these neuronal representations, and as long as we're only interested in the distance matrix, we don't really care about what the single voxels are doing, then everything is beautiful, right? The problem, though, is in that random projection thing, because for this to work, the random projections have to be centered on 0 on average. So it has to be equally likely that the weight for a particular mapping is positive as it is negative. And that is not the case if you're working with fMRI data, because we know that in general the association between neuronal firing rates and bold activations is going to be positive, right? So there's extensive work by people like Nikos Logothitis who have shown that in general, as spike rates increase, we expect bold response to increase. So the mapping is not going to be centered on 0. There are certainly cases where the weighting could be negative, but that will not be the case in general. So what happens if we construct our 20 voxels by taking non-negative averages of the original neurons? Well, now we get a distance matrix that does not look like the neural population code. In other words, if this is what we observe, it would not be the right conclusion to say that this is what the distance matrix looks like in the neurons. It's systematically different. And the way in which it's different is interpretable because there's an aspect of this data that I haven't mentioned yet. What's happening here is that the overall activation level in the neuronal population code is actually increasing as you move from the blue guys to the red guys. So although it's too subtle to see in this color scale, there's a subtly larger overall activation level down here than up here. And that population average axis is effectively getting stretched out here such that the blue guys and the red guys are more separated than they should be in the real neuronal population code. And that just makes visible what is in general going to happen in fMRI voxels if something like non-negative averaging is a more likely model. That is, you're going to stretch out things that are shared in the neuronal population relative to the things that are not shared. So for those of you who have worked with RSA, you might be thinking that, well, this is all calculated using Euclidean distances, but RSA is generally done using correlation distances, which implies a subtraction of the mean. So maybe we don't really have this problem when you use correlation distance. Well, you have the problem, but you have it in a more difficult way. So here I've redone the simulation using correlation distance as the distance metric instead. And what happens now is that you still don't get an fMRI RDM that looks like the neuronal RDM, but now it looks different in a somewhat less interpretable way. And what's actually happening here is that the stimuli that evoke small responses, the blue guys, are ending up far from everything else in the similarity space. So they're all sitting here at the periphery of the MDS solution, while the stimuli that had stronger activations are in the center. And this is happening because when you calculate correlation, you are standardizing all of your vectors. And so what that does is that it inflates the noise. If you have a weaker response in a particular voxel with additive noise, the noise will get blown up to a greater extent, and you'll end up with weaker conditions being far from everything else in the similarity space. And the reason why I'm banging on about this is because this kind of result, once you become conscious of this potential issue, this shows up quite a lot in published RSA papers. And it will happen whenever you're calculating correlation distances over a set of stimuli for which some conditions have stronger average responses than others. You can see this, and it's not a small effect. It can show up quite strongly. So I don't think correlation distance is going to be our solution. But if we're sticking with the Euclidean distances, and ideally in real data we'd be using a cross-validated Euclidean distance like linear discriminant contrast, which I don't have time to explain today. What we can do here is we can take the original neuronal distance matrix that we've already looked at, and we can correlate that with the fMRI data, and you see we get a correlation, but it's not perfect. And this is a noiseless simulation, so it really ought to be perfect if our analysis is correct. But we can also take the absolute mean differences in the population activations, so just literally the absolute difference on average between each of our condition. And you see that here, ironically, this actually correlates by itself more strongly with the fMRI patterns than the neuronal patterns did. But what we really want to do is we can do multiple regression, where we basically take the squared distance matrix here and the squared distance matrix for the mean difference. And by taking the linear combination of those two, we can pretty much perfectly reconstruct the fMRI data. So at least under this very simple measurement model case, where the neurons are just random non-negative averages, we can just do multiple regression to deal with this issue and get something that should work, at least assuming that's the correct measurement model. But what if it's not the correct measurement model? Some of you might have spotted already that this kind of measurement model implies that there's no topography to the response, that the neurons are just randomly assigned to particular voxels with no particular large-scale spatial structure. And if there was no spatial structure, then we would have problems with doing fMRI in general. So what happens when there is spatial structure? Here's a second simulation to get at that. So here we have two cases. So here the responses are just binary on or off, so white means response. So here we have a spatially unstructured representation. The stimuli are on the y-axis, the features are on the x-axis. And here's a spatially structured representation where there is some large-scale organization to the response preferences in particular units. And then this time we're going to simulate what happens with the fMRI measurement by just applying Gaussian smoothing to these. So you can think of this as simulating the bold point spread function, if you will. And what we expect to happen then is that when we start smoothing, then obviously the spatially unstructured representation is going to be changed quite quickly, while in the structured representation, at least some features of it will be more tolerant to the smoothing process. So what happens then for the unstructured case? Here I'm plotting on the x-axis how much measurement smoothing there is, and the red line is going to be the fit for the absolute mean difference RDM, while the blue line is the fit for the pattern RDM to the observed voxel RDM. And you can see that what happens is that as you start seeing more and more smoothing in the measurements, you quickly end up in this regime that we saw already, where the absolute mean difference RDM is actually a better fit for your voxel patterns than the neuronal patterns are, which is funny. If we take the linear combination of those two, then across all these different levels of measurement averaging, again, we can get a reasonable fit, so this works. But what happens when there is spatial structure? Well, it doesn't work so well anymore. So even if we take the linear combination, we're still not accounting for the data perfectly. And again, this simulation is noiseless, so we should be all the way up to 1 if we have the right measurement model. But here, as a consequence of having an inappropriate measurement model that assumes a sort of global pooling of responses, we're failing to account for this data. So when you have topography in your responses, the situation is more complicated, and I'll get back to what to do in that situation towards the end. So that's the basic problem. Now let me look at a concrete example of this, which concerns an fMRI study of face coding. So for those of you who are not face processing people, face space is this sort of theoretical idea that individual faces might be represented in a multidimensional space, where at the origin you have the average face that you've ever seen, I guess, and individual faces are encoded as vectors that extend out from that point, where the direction of the vector is going to be conveying identity-related information, and the length of the vector is going to convey typicality information, so how unusual or how distinctive a given face is. So we were interested in looking at how this is coded in fMRI responses. So we constructed faces in one of these face spaces. This is a PCA-derived face space from Thomas Vetter and colleagues. These are some of the images we used. And we scanned people for multiple sessions per subject while they looked at the images in this sort of presentation. So 3D models, you can do these little videos, but that doesn't really matter for the experiments. So if we take the distances in the original phase space and put them into a distance matrix like this one, you can see that we have this nice little arrangement. And the arrangement of the stimuli I just showed you is not theoretical, by the way. This is actually what happens if you do MDS on this matrix. There is a perfect two-dimensional solution. So if we look at the, first of all, behavioral data. So we asked all the participants to rate the similarity of these faces. And you can see that they rate the similarity of the faces quite close to this space. So this doesn't seem to be completely unreasonable that people do rate faces something like corresponding to the distances in the PCA space. However, when we looked at the fMRI data, we got kind of a different answer. So now we have two viewpoints. That's why the matrices are bigger. But you can see that here in the early visual cortex, you get this very strong separation of the two viewpoints. And within each viewpoint, you get this sort of stretching out where the different caricature levels, the subcaricatures, the typical faces, and the caricatured faces are very well separated. If we look in a more face-related region, such as the fusiform face area, you see an almost complete loss of the view selective information, but still a very strong representation of the different distinctiveness levels. So it's almost like this original half circle that we started with has sort of collapsed in on itself, such that only the faces that differ in distance from the typical face are very distant from each other, while the faces that differ only in which direction you're moving in phase space are relatively less dissimilar. And this was very confusing to us initially. But to account for this, we came up with a few models that include this concept of measurement modeling. So here is one of these neuronal models. This is inspired by work from Frywald and Sau and colleagues who proposed that single units in macaque face selective cortex have these sort of response preferences. So they respond more to a particular direction in phase space, and they don't respond so much to the anti-phase, sort of opposite direction in phase space. And what might be happening then if you have an fMRI voxel is that you're going to have this cell, but you're also going to have a cell that likes the opposite phase space direction. So really what might happen is that you're just pooling all of this out, right? So you end up with coding only how far a face is from the origin with no information about which way in phase space you're moving. In practice, we might expect to see some sort of intermediate case. And here, so here's the full model in 2D. So we have lots of neurons that respond to particular phase space directions. And then we're going to fit the strength of this measurement pooling effect. And here we used a nonlinear method to do this, but in principle, you could use the multiple regression approach that I just proposed to you. So we have a global pool here, and then we're just going to fit the pattern effect and the pooling effect as a multiple regression problem, and that would give you the same answer as what I'm about to show you. So we're going to do between subject cross-validation of this to see how well we can perform relative to the noise levels in the data. And I'm going to show you the data two ways, either with this kind of measurement pooling effect or without it. So the conventional RSA would be that you don't worry about the measurements, and that would be the outline bars. And you can see here in the fusiform face area that this model fits better if you have this measurement pooling effect in there than if you don't. And either way, it fits better than just working with the Euclidean distance matrix by itself. There's many more results in this paper that I can't talk to you about today because we'd be here all day, but the story is a little bit more complicated. Do take a look at it if you're interested. But let me just wrap up by some general recommendations. So what I hope to have convinced you of is that the neuroimaging measurement, in this case the fMRI, the fact that fMRI pools over different neuronal tunings, has an effect on the representational similarity that you observe in your RDM. How much of a problem you have in your data set depends on what the neurons are tuned to. It depends on what sort of measurement you have, if you have a topography of the response or if it's just random mixing. And it depends on where your stimuli are positioned in that neural response space. So in our case, we may have been especially sensitive to this. If you don't have a topography, if you're happy to assume that you don't have a topography, then you can just do this multiple regression trick that I just talked about. If you do have a topography, for instance, in retinotopic cortex, you might need to do something more sophisticated. One thing you could do there is to apply Gaussian smoothing to your neuronal activations and try to tune the size of that smoothing kernel to get an optimal fit. That might be one simple way to handle it. But it would require you to be a lot more explicit about what your neuronal topography really is. I think most models we're working with don't have very specific predictions at that level yet. That's something I'm working on at the moment. If you switch to correlation distance, you'll not get rid of this problem. You'll just have something that's a lot harder to detect. And a result that I haven't had time to show you today is that the general take home of all this stuff, I think, is that if you're working in these sort of multivariate pattern spaces, it's tempting to just stick with that and forget about the activations, but the activations do tell you stuff, and it's always worth going back to do some very simple activation level comparisons to check what's going on there before you go into the beautiful similarity space. That's all I have time for today. Thank you very much for your attention.